Good afternoon, everyone. Today I'll take you through the SOLIDWORKS PCB webinar on design your mechatronics and IoT products easily with SOLIDWORKS PCB. I'm Gopinath KVNSN. I'm a technical manager for SOLIDWORKS PCB India. Okay, so let me discuss on the agenda for today. So we will see on how internet evolution has emerged and typical industry, IoT applications, Internet of Things, how it is going to be influential in our future electronics or the business trends. And we'll see on ECAD-MCAD collaboration, traditionally how it can be done. And we'll also see the design challenges on electronics, the basic electronic industry which they are currently facing it, and we'll have a quick SOLIDWORKS PCB demo, seamless collaboration in the SOLIDWORKS PCB demo, and we'll end up our session with SOLIDWORKS ecosystem and questions and answers. Before going to the actual discussion, let me introduce myself. I'm Gopinath KVNSN, working as a territory technical manager for SOLIDWORKS PCB India. I've got around over 16 plus years of experience in the industry, including 11 years including design manufacturing companies, which typically includes rail rolling stock, rail transportation, and also marine engineering. I had been with SOLIDWORKS community since February 2015, and my basic expertise on PCB tools are SOLIDWORKS PCB. Okay, so let me take you through today's presentation quickly. Before going to the actual discussion, I would like to give a glimpse of how is our electronic design automation today and how it is going ahead. So when we see the electronic design automation for PCB, so as per the experts and from the internet, as we have collected the data, the EDA for PCB to grow at a CAGR of 3.27 during the period 2016 to 2020. Who are all the market drivers for this? What is causing the PCB evolution for the electronic design automation the way we are seeing the aspects today? It is the increasing complexity in semiconductor design and miniaturization of the enclosure shapes. It might be a minute mobile phone which you are holding it, or a kind of a Wi-Fi router, or kind of a device or a PCB which has to sit inside a portable device like a camera or anything. Increasing demand in the collaborative designs and effective solutions. This is also another cause. As we see the electronic design automation, tools are used to design various electronic systems that typically include chips, ICs, microcontrollers, microprocessors used in computers, mobiles, printing technologies, audio, video, medical devices, satellites, including satellites, etc. So products of this kind basically requires the coordination between the mechanical, electrical, and software engineering more than the products less than a decade before. Companies that are making their products smarter, as we see the customers, when we meet the customers, when we have an interaction with the customers, as we understand from them, the companies that are making the products, these kind of products, I can say smarter products, are minuscule, very minuscule in percentage. That means the majority of the electronic design industry has to take a big leap or a big transformation towards designing their mechatronics based or IoT based applications to meet the future generation needs. To successfully take the advantage of this opportunity and transform the products into intelligent systems, basically most of the companies are embarking on a journey to perfect development and the deployment processes to manage additional complexity into this. What is the market here? What are the different market challenges in this? Inconsistency in the manufacturing processes, repeated designs. This is a market challenge. Incompatible tools. That means across different engineering disciplines. The engineering discipline, if we walk in to an engineering company, where we will see the electrical designers, mechanical designers, and the pneumatic designers, hydraulic designers, and the purchase guesses. There are various departments involved in a product design company. They might be using a different softwares. It might not be a unified and then unique software from the same vendor. Compatibility is the biggest concern here. So that is going to be a biggest and then bigger market challenge in today's world. The market trend now is very high requirement of the semiconductor and the memory circuit PCB designs, as we see. Okay, let me quickly explain on the evolution of the Internet of Things. So as we see, with the advent of IoT in early of this 2000th century, 2015 onwards, I can say, with the advent of smart and IoT connected technologies, which normally enables unprecedented innovation, the opportunities and growth potential seem limitless. There is no limit, absolutely no limit, which I'm seeing it as being a product manager, meeting several customers who are making smarter and the smarter products, which we are using or which we are going to use for our future generations. Technology has become so critical, almost like as per the statistics which we have taken now from the various designing agencies, 52% of the companies developing smart products fear losing the market's share unless they continually make the product smarter. They're actually fearing, because if they don't make the product smarter, they will lose the market opportunities. And above of it, 47% worry about the reduced revenue. Why the reduced revenue is happening? Just because the products which are getting manufactured today might become obsolete after 3 or 4 years, because the revolutionary designs, revolutionary trends which is coming up in the electronics design scenario now. So earlier we used to have connecting systems. There are fixed internet systems. There are millions of devices which used to connect from home to automation, industrial automation, and then various other sectors in and around the world. Again, we have ventured into connecting devices where mobile and then cloud has taken place, taken the majority of the designing and the database space. The billions of devices have been connected using the connected devices. That's where we are living in currently. And what we are aiming, or what we see in future, is a connecting world. It's going to be the Internet of Things, which is the buzz word which is using by the industry currently. So which we will see tens and billions of devices, equipments, vehicles, industrial automation devices, home automation devices. Everything in the world is going to be connected smartly using an app-based applications and communicate with the devices directly to reduce the cost, effort, and also the maintenance and other relevant activities. So IoT of things is going to rule the world in the coming years, which I can see. Okay. So as we see, the worlds of mechanical and then computer aided designs, MCAD, and then electrical CAD designs, the barriers are very near. They are closing very small. So let us see what is there in the mechatronics design. So this is kind of a parrot drone which you are seeing on my screen, where it has got, if you just imagine, it includes the mechanical design, it includes the plastic design, it also includes the electronics design, and it includes the electrical design, which need to connect the PCB board, which you are seeing it here, need to control the motors which is running to fly this drone, this industrial drone or agricultural drone, to take some pictures or to read some data from wherever it has been projected. So this kind of a device is typically having power source, embedded electronics, and also having a mechanical assembly, kind of a sensors to sense the object at a height, altitude, and the speed and other related relevant informations, and GPS radios where exactly it need to go, the direction point of it, and also interconnect from the PCB to the motors to drive in a desired direction with a required speed and ability. So this typical product of a parrot drone, which typically includes various design engineering aspects. People who are involved to design this kind of a content, this kind of a product, is the mechanical engineers who's doing the basic outsketch of this mechanical model. They'll do the 3D modeling, and then electrical engineers who are also making the harnesses which need to run from the PCBs to the motors to drive it. And there are PCBs which basically pumps up the power supply and also controls the drone in desired directions and desired functionality. And the plastics which makes the actual manufacturing of this drone to make it usable by the users. So one complete product can involve many of the engineering departments to make a complete product. Okay, let us see traditional how ECAD MCAD integration will be done. So for this example, I have taken on the mechanical side, SolidWorks I have taken as a software, and on the PCB layout side, I have taken ECAD, any ECAD, which we are doing it currently. So how the process traditionally has been followed between engineering teams like electronic and mechanical. So the mechanical, imagine that first the mechanical engineer has designed the case here, and then he exchanged the case design as a form of a DXF file to the electrical engineer. Again, the electrical engineer, he will do the board outline, and he will send it back to the mechanical designer. The mechanical designer again in the format of DXF, and then he'll take that design from electrical designer. He'll do the board outline and constraints, and he'll send back in a DXF format to the electrical designer again to place the components in desired positions. And then the electrical designer again he pushes back this design to create 3D boards at the mechanical side. Again, it comes back for the revised placement if at all any changes need to be done on the placement of the components, routing, or any other aspects of the electrical design. And then he again pushes it back to the mechanical for any interference checking. And finally, the routing can be done at the electrical design, and after once it is done, the manufacturing, then the board will get it fitted inside the PCB assembly. The final assembly will make it. So if you see it, almost like 1, 2, 3, there are 6 number of iterations in the format of DXF will be getting exchanged between the mechanical and the electrical designers in this aspect, in this particularly. Okay, how do we address these things? So let us see what are the typical design challenges that the designers, the electronic designers, CAD designers are facing in the industry currently. One of the primary aspects of the design challenge is the lack of design visibility. Electrical designer will make some changes on the schematic, making some changes on the manufacturing part, he's making it, and the footprint he's making change. And then the mechanical engineer, he might not be getting the same information what the electrical engineer does it. Lack of design visibility. The mechanical engineers assumes as per their mechanical instructions from their boss, and then electrical engineers work as per the instructions and the guided lines and the electrical sense. The lack of design visibility is the biggest concern or the biggest challenge here. Next comes the library component management. As majority of you know, the electronics designers, the ECAD designers, especially they spend almost like 50 to 60% of their time spending on the library content. Either they will be downloading from the manufacturing website, or they will be going ahead and searching over the internet to get the right part on the footprint to get onto their library. So they will download it, and they spend a lot of time to configure it and then again pull it back onto the design space. So library component management is a biggest challenge. And while if you have the legacy data, that means we have a previous projects in a different software, in a different file formats, which we wanted to use it in our current design, there could be issues facing by the electronic designers while importing the data and translating the data. There could be data in synchronization. Data cannot be synchronized. There could be some missed out data. Either might be pads or might be some components missing if the part and then schematic libraries has not been linked together while exporting from the other software. The designers will face the translation errors, the data errors. PCB board fitment issues. So once the PCB has been manufactured and then it comes back to fit inside the electronic enclosure, any kind of an equipment, it might have the problems it can be faced, like the mounting holes might not be fitting inside, or the chamfer is a little bit maybe 1 mm or 2 mm difference is there in the chamfer. The keyboards are not fitting, the mounting holes are not fitting, or the component height after closing the top cap of the upper lid of the electronic enclosure, there are some components which are getting obstructed, interfere with the top cap, or some components have come at the last and then it is getting protruded from the side of the PCB panel. So there are fitment issues which designers might get experience once the board get manufactured and then it is getting fitted inside the electronic enclosure, which is crucial. And as the design limitations are going faster and faster, as we see, the design complexity is getting increased, high pin count and then package density. So there are ICs, BGAs, ball grid arrays, which we are seeing in a microcontroller, microprocessor controllers, and the DDR RAMs or motherboard kind of circuits, where we see very high pin count, more than 100, 200 pins, which we need to configure it. And we need to manage the package density. So this is a high design concern in the electronic devices. And the biggest, toughest challenge which the industry which currently is facing is the electronic and the mechanical CAD design integration. Electrical team is working separately in isolated world and the mechanical team is working separately in isolated world. They will be just discussing, they will constrain everything on their own specific requirements, and once they put both these designs together, there is an asynchronization between the data which they prepare it. So electromechanical team collaboration is the biggest concern, biggest challenge. Above all of this, the quality and the reliability and cost is going to be affected. The quality is going to be degraded, reliability is lost, and sometimes the cost is going to be increased because the number of iterations, the number of mistakes, the number of mismatches while exchanging the data between the electronic and mechanical CAD design teams is increasing the cost, because the designers has to sit more time to eliminate the errors, to reduce the errors, and then to make the PCB functional. Fine. So we have seen what are the different challenges which we have it today in the electronic industry. Now we see why a SOLIDWORKS PCB is required. SOLIDWORKS PCB is an automated software, independent automated software powered by Altium, having a capability to design the schematics, PCB layouts, as well as the mixed mode simulation. So using SOLIDWORKS, we can design with a high visibility in the design, because the electronics and the mechanical designers are communicating, collaborating, integrating their designs dynamically in real time. By doing so, we'll be minimizing the iterations which is going to happen between the electronics and the mechanical design teams. Using SOLIDWORKS PCB, the enhanced libraries and the database management. SOLIDWORKS PCB supports symbol wizards, inbuilt symbol wizard with a various design shapes of connectors, ICs, and various other symbols can be configured inside SOLIDWORKS PCB. And huge database management supporting libraries make SOLIDWORKS PCB robust. We can also link the databases, external databases like msaccess.mdb file inside our SOLIDWORKS PCB and can collaborate. SOLIDWORKS PCB supports in the native design exchange file. We don't need to exchange any external files. SOLIDWORKS PCB uses exchange the data natively. There is no external file which is floating between mechanical and electrical teams. It has always been a native file exchange. There is no need to exchange the file. It is all inbuilt feature which will push and then pull the designs from electrical and mechanical teams. We can define, the users of SOLIDWORKS PCB can define the board shape directly from MCAD and collaborate with ECAD, so that it is very easy and constraint defined by the mechanical engineer as per the casing, and there is no scope for error in this. SOLIDWORKS PCB includes IPC compliant footprints and netlists. So users can easily define their basic shapes like ball grid arrays, electrolytic aluminum capacitors, a dual flat no leads, or a transistor outline, or a land grid arrays. So different components which normally we use it for high-end designs, high-end PCB printed circuit board designs can be done using the IPC footprint, compliant footprint. And we will also see a real-time electrical and mechanical collaboration using SOLIDWORKS PCB and SOLIDWORKS window. So we can dynamically position the components wherever it is and route the components wherever it is from the ECAD side, and then push those positions and along with all other data from ECAD side to the MCAD side. So MCAD, the mechanical designer, can move the components, can apply his own mechanical constraints onto the PCB board using SOLIDWORKS 3D CAD, and pushes it back with his constraints, writing all these details in the collaboration window and send it back to the electronic designer, and then he can visualize before accepting it. And with the above of all these features, we can achieve using SOLIDWORKS PCB better quality, reliability, and then cost-effective solution, because the number of iterations between the design teams is drastically reducing using SOLIDWORKS PCB solution. Okay, what are the key values of SOLIDWORKS PCB? So as we see here, the electronic and the mechanical CAD designers and design teams can collaborate dynamically in real time without having any external file exchange. The cross-discipline flow is being achieved. Component data management using a huge database and support of Altium. And we can also constrain the layout in SOLIDWORKS PCB as well. And we can also do it in SOLIDWORKS 3D CAD. Circuit simulation, mixed mode circuit simulation can be achieved using SOLIDWORKS PCB. Electronic and mechanical CAD engineering change orders can be reduced, minimized drastically to improve the quality, performance, and then productivity, and reducing the cost and meeting the timely deadlines. What are the various advantages? Seamless collaboration and very less design iterations, as I have rightly indicated a couple of minutes back, and we can also do the PCB design with high accuracy and precision. So as I see, what are the typical capabilities? Using SOLIDWORKS PCB, we can create schematics. A traditional 2D PCB layout, we can transfer the schematic relevant symbols onto the PCB layout space and position the components and do the routing. 3D PCB visualization and layout. Instead of going to the 3D CAD, we can also visualize the 3D components, interference, everything in SOLIDWORKS PCB 2D alone. This is the visualization. We can do the mixed remote simulations by simulation using SOLIDWORKS PCB, SOLIDWORKS mechanical collaboration. So once we have done the PCB from electronic CAD side, we can push this PCB along with the components into the mechanical side and do the modifications as per the mechanical constraints using SOLIDWORKS. We can also do the design, compare, version control, and final bill of material and outputs, Gerber outputs, etc. So let us quickly start how effectively we can do the SOLIDWORKS PCB demo. What are we going to see is we have a basic design workflow for SOLIDWORKS PCB is the ECAD MCAD collaboration. We'll define the layout from MCAD and do the seamless collaboration. And when next we will be going to the schematics and the library management. We'll create the small schematic and then do the library management and all. PCB layout and rules constraints is the third step in our demo. And finally, we'll come to the fabrication outputs. Okay, so let me just show you quickly on SOLIDWORKS PCB what are the different aspects of it. Fine. So as I rightly done, so I'm going to show you this is a typical SOLIDWORKS PCB design environment where we do have the project relevant tabs. We have the whole circuit elements to add the different circuit parts. We also have the power ports like a ground and VCC and other power point like 12 volts plus 5 volts, etc. We also have the directives if no connection has to be added onto your PCB components and your design window, and also various harness and electrical control cabling relevant details, sheet entries, graphical elements. We also do have the system relevant folders and zooming windows. In project, we can add a new schematic, new PCB boards. We can generate outputs. We can control the variants. You can control the variants. You can import, export designs, templates, project options. We also do have a simulation options. We can set up a simulation setup, and we do have like different analysis like operating point analysis, transit analysis, DC sweep analysis, AC small signal analysis, noise, transfer function, pole zero, parameter sweep, Monte Carlo analysis, like that, global parameters. We can use this XSpice simulator once the circuit is done. Similarly, we also have the outputs, electrical rule checks and report single lines. And when we are in PCB, we have the PCB editor, design rule checks, PCB constraints managers, compilation and errors, connection matrix, and various other options to make our SolidWorks PCB tool robust. What I do quickly is I'm going to show you a quick demo of adding certain on SolidWorks PCB. As we see, this is a hierarchical design, so we have a number of sheets in this particular project, and this is a condition relay schematic. This is a buzzer, and this one is a power schematic to power up, to give the 12 volts power to the other parts of the PCB, and this is a stepper motor controller. And we also have a default board layout. What we do now for this particular project, PCB web demo, what we'll do is we will go to the mechanical, SolidWorks mechanical, and we'll define the layout from SolidWorks mechanical as per the enclosure where the PCB is exactly need to be fitted in, and then drive the design, the layout from the mechanical to electronic side, the EDA side, ECAD side. So let me minimize this window and then go to SolidWorks window. So this is my SolidWorks 3D CAD along with SolidWorks PCB add-in, so that this collaboration window will enable us, the mechanical engineers and then electrical engineers, to communicate to and fro, pushing and pulling the designs between the design teams. Okay, as you see, so this is the default board which I have in the mechanical thing. So what I'm going to do is I'm going to make this shape exactly same as per the enclosure. So what I'm going to do is I'm going to insert a component which is a drone assembly. So I'm going to insert the drone assembly here. So I just wanted to take the board exactly the shape as per this one. Okay, so what I'll do is, so I have got the drone, a typical parrot drone something, which I have inserted. So what I'm going to do is I'm going to mate this constraint on top of it. So let me just quickly select both the surfaces. I'm going to mate these two surfaces into this, say OK on this, and close the mating. So I have got, let me just put it in the front view of it. I've got the board shape defined here, but I don't want to see my board shape like this. So as you are seeing, so my board shape has to take the top upper surface of the drone. So what I'm going to do is I'm going to go to the edit sketch. I'm going to remove this, the default board sketch, and I'm going to select the board shape in 3D sketch, which has already been defined as a board profile in the drone. So I've just selected the board profile here, and using SolidWorks feature convert entities, I can convert this particular 3D sketch into a PCB layout. So let me just use the convert entities and then close it. Awesome. That's it. Job done. I mean, we have done almost like couple of steps, only 2 clicks to just make our board exactly fitted on top of this drone. So this is going to be a PCB board defined as per the shape of the drone. So if you see it, there is one more PCB which is there inside. Okay, so let me just put it on the front view of it. Let me save for the time being. Let me save this configuration and save it here. So I just wanted to push this board from the mechanical designer window to the electronic designer. So what I'm going to do, I'm going to use the PCB add-in, which is a SOLIDWORKS PCB services, which enables the collaborative server, which enables the mechanical designer to communicate his design intent to the electronic CAD designer. So let me just push this, that I'm going to write that board layout defined. The moment I say board layout defined, so this basic board will be going and sitting onto the electronic designer's design space. Let us go back to the ECAD side, that means SOLIDWORKS PCB side. So as I said, so we are again switching back to electronic CAD designer side. So this is ECAD SOLIDWORKS PCB. So this is a default shape. So let us see what is there, how does the communication happens. So the moment I click this SOLIDWORKS PCB connector, SOLIDWORKS PCB connector is a collaboration server, which is an add-on application by default will be added to SOLIDWORKS PCB, which enable the communication between SOLIDWORKS PCB and SOLIDWORKS. Okay, so let me just notify here, there is some message sent by admin. So we can see if two users are connected in two different machines connected through a company intranet, their system names or user names can display here, will be displayed here. Fine, there's a board layout defined indicated by the mechanical engineer. Let me see what it is. Let me see the changes. So there are some changes which he has already been defined. One is the board outline. Second is drone. That means the drone which the mechanical designer has added into it. So that is also coming. So let me just select the drone. I can take it later. I will select so you can see it, the pink color which is being indicated here, which is an indication that the green board, which is the default board, which is a rectangular shape, is going to take the shape of the pink color shaped PCB, which has been suggested by the mechanical designer and which is desired one. So let me just check this, accept it. That's it. My PCB board in SOLIDWORKS PCB will take less than a second to take the shape of the enclosure defined by the mechanical engineer and then exchanged. Have you noticed any file has been exchanged here? No, absolutely no. It is a native file exchange, native SOLIDWORKS based format which is getting exchanged and then which can be kept inside the folders at the back end. So we don't need to worry. The users don't need to worry at all while doing in SOLIDWORKS. So next what I'll do is I will quickly select the origin and then I'm going to put this origin somewhere here. Okay, now my layout has been ready. Let me just save this configuration here. I'm going to the tools, view, and put this as a zoom all document. So right, so I'm going to make some changes on the schematic now and then I'll go in a quick pace to demonstrate the rest of the demonstration. I'm going to the stepper motor and I'm going to add the libraries. So let me add the libraries. Let me quickly select the library, the relevant libraries. I have got various libraries which has been loaded here. I'm going to select the stepper motor library. So what are the missing components? So let me see some of the missing components I need to add it from the library. So which one is a potentiometer? Let me just double click it and then add it from this. So and couple of capacitors which is 10 nanofarad. So let me just quickly, and we can easily change the direction of the components while placing using the space bar. So let me just click this. So these two components have been created and one more junction connector which has also been added together in this. So I can add this component, I can change the direction of it. You can see the direction of it using a shortcuts. So we can just move the pins also. You can see it is starting from 6 to 1. Now it is 1 to 6. So you can easily change using the shortcuts using SOLIDWORKS PCB. So let me connect it quickly here. Okay, so let me just press the escape Okay, so I have pretty much done on the schematics. I have just added a couple of capacitors, one junction connector, and then one potentiometer of. But what is remaining? So all the new component has to be annotated, because as you see, all other aspects, the design intent, all the design elements have already been annotated. The new elements have not been annotated. So let us quickly go and then annotate the schematic. There are various ways to annotate the schematics. We can choose the order of processing based upon the components placement. So it will take automatically, the numbering can be done based upon the pattern which we are choosing it. So you can choose up, then cross. You can also choose down and then down and then across, then up. So different patterns will decide that based upon the components placement. The designations of the components can be named. Okay, so I'm going to update the changes into the list. So there are 4 elements which has been added. It is going to take accept the changes. I'm going to validate the changes. Validate the changes is the we are proposing. These are the names need to be added, and execution of the changes is this design. The changes have been implemented onto the schematic space. Let me just close it. Yes, this has been implemented as per the position of the components placed on the schematic space. Now we have already done on schematic space. Okay, let me just save on this. You can also compile this project, so you will have the compiling errors, and then some of the components doesn't have the no driving source, and some of missing negative differential pairs. So some components having issues. So these can be eliminated using project options. So there are project options which are available here. So there we will be defining a specific rules for compiling errors, compilation of errors. Imagine that if, let me just go here, the floating point inputs, I will just say that instead of error, I will say that no report. And nets with a no driving source, instead of a warning, I will say that no report. So once I confirm these things, I can also check some of the rules which can be put it in the connection matrix also. Once I have done this, let me say OK on this, and if I recompile it, number of errors is going to be reduced. You can easily see it here. See, the number of errors have been reduced now. So similarly, we can eliminate all other errors based upon the rules and the connection matrix and rules and constraint editors. Fine. So what we'll do quickly is we have got the PCB layout. We have compiled, and we are going to quickly import the changes from the schematic space. We'll be executing the changes, validating the changes, and executing changes so that all the reference components footprints will come along with the nets in this. Let me just close, and then I have got a plenty of components which I need to just quickly arrange here and drive it. So let me just arrange these components somewhere here. I just wanted to add this component somewhere here, and this is a PCB which I wanted to have it, and these are the 2 connectors which I wanted to place it at the extreme ends, and one more IC. I think this one I just wanted to pull it at the back side. You can see it. This I have pushed it at the back side because the designation has been flipped. I can also show you on the 3D visualization. Fine. So let me just add this component somewhere here, and the other 3 elements I just wanted to put it here, and these I'm just driving, and you can also rotate these components as per our requirement. So let me add these 2 things here because this has got more connections at this place. Similarly, I'm going to add these 2 things here, and adding these 3 things at the back side. So we can just push the components wherever we just wanted to have it. See, I'm just adding these components somewhere here, and these components I'm just pushing it at the back side. So I'm just placing the components wherever I wanted to have it. So let me just place these things here in this layout. So let me just take this. There are 4 more remaining which I can place it and distribute it as I required it. So wherever I have more number of components, I can easily distribute them as per the required spacing. Fine. So I have got all the required components which has been already added. You can see that interference, once I bring on component, this is getting interfered with other components at the back side. So let me just adjust if the interference is bothering us much. So let me just rotate the component here and place it somewhere. So let me just add these components here. Let me just adjust this one. There is one more resistor. Yeah, I wanted to put it like this, and this one also I just wanted to adjust somewhere nearby. Okay, so we're pretty much done on placing of the components. Let me just place this component. Let us quickly see how we can push this design to the mechanical design space. Fine. Let me save this configuration and go to view. I'm going to push this design to the mechanical designer. I will say that components placed are positioned. Instead of placed, I will say that positioned. I'm going to post it. So before saying that, what it says? It says there are some duplicate component designators detected. So all these things are coming as per the rules defined in the PCB editor. So there are R1, Q1, C1. The component designators must be unique. So what we'll do is R1, Q1, C1. We will quickly find it out and then eliminate it. So this is C1. We'll just take it out. Q1, which is a duplicated one, and R1. So we will take these things out. So let us try now. Components positioned. Let us post it. So it is pushing now because the software finds the duplications of the footprints before sending it to the mechanical designer. So this is a kind of a design rule checks which we want from the electrical design or from the mechanical designer when they are exchanging the data between the other teams. They should be 100% sure that the data which they are giving is validated data. Okay, so we have got this PCB layout which has been defined here. Let me just save it, this one. Let me go back to the PCB. Okay, so what is there inside? So let me just see components positions, whatever the electrical CAD designer who has communicated. So the same message which is displaying in the mechanical CAD designer's window. Let me just see what is there in it. Okay, there are various components which has been added into this. You can see this, all these components have been added. So let me just check all of them, accept it. So once I accept it, all the 3D equivalents for the footprints which has been positioned onto the 2D PCB board in SOLIDWORKS PCB, the equivalent 3D parts will be pulled using the collaborative server. The standard 3D elements will be populated onto the PCB board here. So that's what we are going to see it in SOLIDWORKS 3D. So once the process is completed, we will see it in the SOLIDWORKS 3D. So let the process complete. So once the process is complete, we can see it, these things here. You are seeing it at the back side. All the components which we have positioned on the drone in the mechanical model as proposed by the electrical designer, that we are seeing it on our screen. Yes. So you are seeing the components positioned by the electrical designer, electronics designer, in the 2D space, the same components, the 3D equivalents of the components, which we are seeing it here with the decals associated with it. So you can see the push button switches. Here you can see the connectors, you can see the ICs, and you can also see some of the components at the back side of this board. So let us save this configuration here, and you can quickly make some changes onto this board and then push it back to the mechanical designer, because the mechanical designer just wanted to have a quick adjustment onto this, because the moment the electrical designer, as you see, make the changes and he has positioned the potentiometer as you see here, he doesn't know that whether this is going to be interfered with the screws which need to fit this PCB board to the following structure in the drone. So this need to be adjusted. So what we can do is we can just right click, move this component onto a design space. Similarly, we can also flip the components using the PCB add-in, we can flip the components at the back side. So this component has been flipped. So a couple of changes which we can make it. I also wanted to have a little bit movement on this one because this is also obstructing a little bit. All these decals also can be adjusted once the couple of iterations has been happened. So you can adjust these components using a scale based pattern. So you can see it, you can also adjust whatever the distance which you are moving it. Imagine that we just wanted to move it as a 2 mm distance or 2.1 mm distance. So that distance can be indicated over here using the scale. So now all the three components have been adjusted and a couple of other components have been flipped at the back side. And also I just wanted to save this configuration before sending it to the PCB side. I just wanted to make a couple of holes on this to just accommodate these holes into the PCB design side. So let me just open the board, this PCB board, and I just wanted to make the couple of holes onto this. So as I see, I can just add a sketch onto this and made a hole in between the components. I'll make it as 2 mm. Say OK on this. So let me just adjust this hole somewhere here and go out, go to the features. I just wanted to cut extrude. So let me just say OK on this. So I've made one hole on this. We can make n number of holes. We can also use the linear and the circular pattern to make the holes onto this. Let me just save this configuration, save it. So once I have done this hole, and it will reflect, the same will be reflecting back onto the assembly wise also. Fine. Now let me save this configuration, and along with all these I will be pushing back to the electronic designers. C6 flip and J12 J3 repositioned to X is equal to 2.52 mm, Y is equal to 1.5626 mm. So that's what we were indicating. All the design aspects, the design intent can be communicated using this window. And potentiometer RV1 repositioned. X is equal to 2.35 mm and Y equal to 3.56 mm. So this is the kind of a communication which we can easily communicate, and this will be recorded inside this SOLIDWORKS PCB add-in. So all these things, whatever the design intent being communicated between the design teams, will be retained as it is here. You can see it here, and we can recollect it, who has communicated what. Fine. So let me just go to the 2D design space, SOLIDWORKS PCB. So the same thing, whatever the intent he has communicated, all these things without having an external communication, without having a phone call, without sending this information, these files, any external files through an email or a over table discussion, nothing of that sort will be working here. It is only a dynamic real-time communication collaboration between the electronic and the mechanical CAD design teams, which is an awesome feature for any CAD designers, any PCB CAD designers which they are looking into. So that can be achieved using SOLIDWORKS PCB and SOLIDWORKS platform. Let me just view the changes. So there are various views. You can see it here. When I click this RV1, you can see the animation of RV1 which is coming down to a distance which has been specified. Similarly, the other aspects of it. So let me just check all instead of a drone. Just let me just accept the new positions. So it has taken the new positions. You can see C6 or C8 which has been taken the back side. It has been flipped. We also have J3, J2, J1 has been repositioned, and there is one hole which has been there. So what we'll do from the electronic designers, we will just remove this hole to the other side, because the electrical designers just wanted to have this hole to be shifted to the other side of this. So let us quickly see the 3D PCB visualization inside SOLIDWORKS PCB. How does it work? So see, this is a quick 3D visualization of a PCB board in SOLIDWORKS PCB side. So before going to the actual 3D SolidWorks content, we can see it. We can also see at the back side of the board, there are 4 or 5 different components which we have pushed it back at the back layer. So we can see it at the bottom layer, whatever the components which we have positioned, and in a single layer mode, we can see it, all the components. So let me go to the top layer, go back here, and what we'll do now is quickly do the routing. So what are there in the routing? So we have in the home button various design rules. We also have various design aspects, and we can redefine the board shape, move the board shape, edit the board shape, everything can be done. Let us go and then see what is there in the design rules. So in the design rules, PCB rules and constraints editor, we have the electrical rules, clearance rules, short circuit rules. We can define the routing widths. You can define a new routing widths also here, and then rename this as a +5 volts width. So you can define a specific width pattern also, and then when you double click it, it will be having this information inside this. So before this, let me just change this metric units to metric, so that it will be easy for us to proceed further. So let me go and then show you. This is a routing widths can be defined here, and it will be showing here, and this will be editable. If it is not 2.254, it is 0.24. You can easily make these things. These changes. Routing topology can be defined, fan out control, routing via styles, differential pair routings, SMT mask, planes can be defined, power plane connector style, test points, assembly and then fabrication test points can be defined, the rules can be defined inside this, and even power plane clearances, plane connect. We can also give the thermal relief connect for the power, ground, or any other kind of a wires which we are going to add. Either it may be micro wire, it may be buried wire, or it can be through hole wire which we are using it. We can also define the component clearances here. It's editable format, so which can be edited, maximum vertical and then horizontal references. Okay, so once we have done these things, let us go and quickly do the routing. So there are 3 types of routing. One is interactive routing, interactive differential pair routing, where we have a kind of a power supply plus minus voltages, or high and the low end voltages, which is originating from one transmitter and then going to the receiving device. So those two can be done with a differential pair routing. And if you have a connector which is getting connected with an IC, all the 4 or 5 pins, we can use the multi-pair routing also. So let me just quickly select and do the quick routing of the components. So where can we do? So let us just go and then check this. So you can see how much width which we are going to run. It is going to show us. So I'm going to insert a, and it is going to be connected, because as you see, so to connect from this rubber band which is originating from this 4 slip, this width, connecting to the R19 which is there at the back layer, which is the bottom layer. So we need to have a wire need to be added quickly to get it connected. So this is how we can do the interactive routing using SolidWorks PCB. Let us just quickly see how we can do it, the routing, interactive routing for the other components. 1 or 2 components we'll see, and then we'll go ahead with the other routing parameters. Okay, so let me just connect these things somewhere here. So this is how we can do the manual routing. So we will also do the automatic routing. So auto route option is also available. We can quickly select whether it's a default 2-layer board or 3-layer board or 4-layer board. We can define it, and we can route all the elements. So once this is done, so it will take by default as per the routing rules defined, whatever the shortest and the optimum routes it will be defining in the PCB design. So once we have done this, then we will quickly go back and see that how we can generate the output formats for this. So we'll quickly share this routed PCB board with the mechanical designer and then see how it can be. Okay, now the routing has been done. So you can see it. The routing has finished with failed to complete 0 connections. So it has hardly taken half a minute to just do routing for a component more than 30 or 40. We can see it in 3D PCB visualization also. So let me just put it across and put it in single layer mode. So once it has been put it in the single layer mode, so this is coming as like this. Okay, we can see the internal plane layers and all other aspects of it in 3D PCB visualization. Okay, I'm coming back to the 2D footprint. So let us quickly see what is there in the layer stack manager. So layer stack manager is the one where we can add a different layers here. So this is top overlay, solder, and then layer, top layer, dielectric is which is separating the top and bottom layers, bottom layer which is the signal layer, bottom solder layer, solder mask layer, and then bottom overlay for the silk screen. This thing. So all these layers have been defined with the defined thicknesses, and the dielectric material has been defined. If any additional layer which we wanted to add it, we can easily add it with add layers here. So the signal layers can be added like this, and automatically the dielectric will be getting added into this. If you wanted to have an internal plane layers for the power plane and the ground planes, which we can do it with an internal plane layers, so it can be added together here. We can also have a 3D visualization by clicking this. You can also have a presets in SOLIDWORKS PCB which enables us to define our layer stack structure. Either it might be a 4 layer which is having a 2 signal 2 plane, or a 6 layers which is 4 signal and the 2 plane, or 8 layer which is a 5 signal and then 3 plane layers, or a 10 layer which is having a 6 signal and then 4 layer. So any default presets can also be there, and we can also save this configuration. Then you can also load it, save it, and then load it again to a any prescribed the required prescribed format into a existing design. So this is about this one. And once the board has been defined, you can also bring in the drill table. So we can just place the drill table inside this. Okay, so this drill table will be having the plated through hole. What is the kind of a hole which we have made, a round type hole, and how many hit counts, kind of a symbol, this kind of symbol, this kind of symbol, how many holes are there, and what is the finished hole size. So everything can be defined in the drill hole sizes. Similarly, we also have the various configurations can be mapped either in 2D or in the 3D configurations. We have all the layers which has been used for a particular PCB design: signal layers, internal plane layers, and mechanical layers, and like mask layers, solder mask layers, and other any layers like drill guides, key port layers and all, and system colors, silk screen layers. That means the signal layers basically. Top layers and the bottom overlay, silk screen layers for the text of the reference designated text which is on the PCB side. You can alter the colors and everything here using the 2D system colors and other configurations. So you can switch off any layers, you can filter layer options, everything can be done it here. Similarly, if you wanted to visualize and see that what is there on the particular PCB board design. So let us see that if I wanted to see that components, where is the power component? When I just click in the PCB, the filtering option will show me where are these components which has been located. So let us just see what are the components which is there in the power schematic. So there is C3, there is C4, D1. So likewise all these components can be seen here and then filtered here. Let me just close this PCB. Okay, I will also quickly show you how quickly you can add the schematic symbol and then PCB symbol. So we have, let me just quickly add schematic library. So one schematic library. So once we add the schematic library, so SOLIDWORKS PCB having SOLIDWORKS symbol wizard, PCB symbol wizard, where I can configure that. I'm going to add pin numbers like 15 as a pin number, and I'm going to select the configuration as quad side, 4 sides. So once I have selected this, and I can also choose the pin which is getting entered, whether it's left, bottom, right, or top. So I can easily choose which pin to be connected in what way. And also I can select that whether this is going to be an input or input output, or this is going to be an output or open collector, whatever the option which I have in this. And I can easily place the components. Whatever the configuration which you have defined, you can easily place the components in this. And you can also write text which you wanted to have it on any kind of a device. So if I wanted to edit this, which is output port, so I just write it here, and so you can adjust these things, and you can double click the text string, and you can increase or decrease the size of it. Instead of 10, I'll make it as 2. Let me just take this as 2, say OK on this. So once I have made this, then you can add it onto the port basically. So this is how basically we can define the text inside this and defining the symbols. Once we have this, we can save this symbol in the schematic library 3, schematic symbol, save. Let me just close it. So you can see these components when I am in the schematic. Let me just close. I will go to the libraries. So I can see that the newly created schematic library symbol, when I double click it and add it, I can add it the symbol onto the schematic space, and I can run the wires from there. Wires are cables from there. So this is how normally the schematic symbols can be generated. So let us quickly see how we can generate the PCB library or the PCB components. So what I'll do is I'm going to use IPC footprint wizard to create the PCB footprints for our PCB footprint library. So IPC footprint, compliant footprint, having a number of components, number of component types I can see, so which will assist us to make our defined components. So there are components like ball grid array, as I explained, chip array, electrolytic capacitors arrays, or chip connectors, or land grid arrays, various other components like flat pack, plastic wad, flat pack. So various components are there. Let us define on the ball grid array. Let me go to the next window, and all the height and every parameter as per the data sheet, as per the manufacturer data sheet, can define here and alter these things. If we wanted to have, it is not 3.5, if it is not 3.5, you can just make it. If it is not 12 as per the data sheet, if it is going to be 14, you can make it. So all these things can be made, alterations can be made to make the possible. And let me just selectively decouple. So I just wanted to make these things. Number of rows removed 3, number of columns removed 3. So I just wanted to make it as 0, 0 here on the add balls to the cavity. Next, all other parameters like pads diameter can be defined, silk screen dimensions can be defined, courtyard and assembly component for a right aspect of the defining the footprint can be defined here. And once we have done all these required aspects of it, we can publish it. So based upon the number of rows and columns elimination, we have got the ball grid array with this shape. So let me just quickly go and save this PCB into the PCB library in the same project directory. So let me just save it, PCB3, library 3. Let me just close it. If I just wanted to associate that PCB footprint to this component as per the configurations. Of course, as we all know, as per the designer, the pin configurations and then the specification of the component should match to map the footprints and all. Let us quickly see, double click this component. I just wanted to add a footprint into this. So let me just go and then browse. And I'm going to see various PCB libraries here. So the one which I have recently created is PCB library 3, PCB library. So let me just select this. I have only one component because I have only created one component at this moment. Let me just quickly see this, and you can also see the PCB ball grid array which I have created just now. Let me say OK on this, say OK on this, and this PCB 2D footprint has been added here. Let me say OK. Please OK on this. So how do we see this component, whether this 2D footprint is coming in PCB layout or not? Let us quickly see. Before that, let us go to this component properties and make it as IC, which I have given a designation for this, and I will quickly go and then annotate this schematic, annotate schematics quietly. So it has taken the designation as U1 now. Fine. Let me just save this configuration. Go to the PCB layout. I just wanted to import the change. So let me just select all of them, and you can disable selected. You can disable selected. So I can just add this U1 to a stepper motor. So let us see if we have any other U1s which are there in our design. So which we have chosen it. Okay. So this is which we have done it. So validate the changes, execute the changes, yes, and close it. Job done. Yes. So whatever the schematic component which we have created and the PCB footprint which we have associated, the PCB same PCB footprint which we are seeing it here, and once this is done based upon our no, the schematic connections, this can also be connected onto the PCB board. So if you want, we can just push this into this design space and then keep it here. So this is how basically we can create schematic library components, PCB library components using SOLIDWORKS PCB and the SOLIDWORKS combination. Let us quickly see how once we push this design, how does we see it in 3D. Let us push routing done. I'm pushing it to the mechanical designer about these components. Once it has been positioned, fine. So I have just positioned pushed onto the mechanical designer. So let us go and then see what is there in this. So routing done. So let me just view the changes onto this and check all the aspects, accept it. What is going to happen? Let us quickly go and then see. We have done a couple of changes. The whole has been repositioned from downside to the upside, and we have flipped a couple of components in electrical CAD, and we also in routed a couple of components we have added into the schematic space. Let us quickly see whether this is applying the space. It is able to bring the tracks and everything inside SOLIDWORKS PCB. So once this is done, so we can see it, the SOLIDWORKS PCB, a completed routed PCB board which is defined as per the enclosure of drone top upper layer, which we can see it here. So before that is done, so let us just quickly see what we have seen here. We have seen drone, we have defined the structure and the collaboration which we have seen, and PCB connector, using PCB connector, how it need to be communicated. Fine. Now we are seeing here all the components have been laid down and with the tracks which are running. So this is a proper PCB design taken place using SOLIDWORKS PCB, and the collaboration with the SOLIDWORKS mechanical teams can be done dynamically. Whatever the changes which we have done, even if you notice it, the decals, the holes, everything earlier it has been not been moved. Now it has been moved to the upper layer part of it. So we have done on the mechanical side. So let me just save it on this. Close this mechanical session and we'll go to the final aspect of it. So what we have seen is in the schematic library management, symbol wizard. We have seen the supplier links, database management which we have seen. As you are seeing it, we have added the couple of symbols using symbol wizard, PCB library footprints which we have used it in IPC compliant footprint, and also the supplier links. So supplier links is one where users, when they are using a particular component, if they wanted to know that whether the component is available with the supplier, so SOLIDWORKS PCB includes supplier links where a particular component with the different manufacturers can be searched over in internet and can check for the availability and then cost information accordingly. So I'm just searching for that IC controller which is having the part number DRV8825BB, having a various manufacturer like RS components, Varial, Aero Europe, Evanet, Chip-on, One Step, like that. So let me just select the Farnell. So this is having an information. If you see in the bottom side of it, this has got information, all the manufacturing information, number of pins, output temperature, operating temperatures, everything. The documents also, it will be having it. That means the data sheets which has been associated with it. So everything it is able to extract from over the internet and can be added onto the schematic space. And also the very important thing, the pricing information in the particular currency of it. So this is about the supplier links in SOLIDWORKS PCB. So let us go back to the presentation part of it. Database management which we have seen and everything else. PCB layout, we have seen the PCB rules and constraints, design rule checks to add it upon, and we have seen the compilation errors. We have seen the PCB rules and constraint editor for vertical and the horizontal clearances, how to define it, and we'll be seeing now bill of material and the fabrication output files using SOLIDWORKS PCB as the final part of our demonstration. Fine, we have pretty much done with our demo. for today. So what we'll do now is we'll go to the PCB and then we'll go to the generate outputs. So generate outputs, we can create variants. Also here we can choose the variant, variant 1 or variant 2, and it will be identified as the configurations also. We can select a specific variant or a default configuration for producing the output variants. Currently we are only going ahead with the default variants. So let me just choose the bill of material. So when I click it, the bill of material is going to be, yeah, all the design aspects and all the columns with an accuracy, category of the components checked by company name. So all these comments will be coming here, adding into this, and I can choose, I can produce the bill of material in a CSV format, XLS format, portable document format, PDF format, and other formats as well. So let me just check this one in Microsoft Excel sheet. The default templates, you can create it, you can select it here. Let me just say OK on this. I'm selecting this schematic prints, PCB prints, and the Gerber files. Yes, I'm going to select as a millimeters and 4:4 aspect ratio for the resolution. And Gerber extended files, I just wanted to select all the layers. As we all know, Gerber extended is an extended version of the Gerber files, and beyond that we also have IPC 2581, which is in a single file format which can be referred by the manufacturers. So that will also have the information about the layers, inside layers, and power plane layers, are the pads, and all other information which is associated with it. So let us select for the Gerber extended all the relevant layers, conductive and non-conductive layers, which is top overlay, bottom overlay, top silk screen layer, bottom silk screen layer, outline layers, bottom paste or top paste, or no, our signal layers, everything. So let us say OK on this. Similarly, other aspects of it, ANSI drill files, we can configure it. What is the configuration, like 2.1, 2.5? You can make it as in millimeters and 4:4. Say OK, and ODB++, 5 to exchange with any other CAD systems. And IPC 25, as I said, 2581. So IPC 2581 version, which we can select it as a B or A version, and choose the metric systems. Floating point correction also, we can just make it here. If it is not 6, you can just make it as 5, and based upon your requirement, then do it. So we can also export this file as a step. We can also export as design rule checks and electrical rule checks, but currently we are selecting the export step and then AutoCAD DXF file also. We can also export this layout information into AutoCAD files using from R12 to R2013 in a DW or DXF format with imperial or metric units and as a blocks and other information. So let me just quickly select and generate. So this will generate the required output configurations, output files, and it will be getting all these files once it is generated, which will be appending to the configurations at the project configurations. So let me, before this comments, let us go back quickly what we have seen. Bill of material, we have configured this configuration of the bill of material and other Gerber files, NC drill files, and extended files. What are the typical PCB applications? What we see, SOLIDWORKS PCB can be used in any of these kind of an applications. Either it can be in marine applications or aerospace applications, or in non-conventional energy like the windmills and all, and kind of our mobile smartphone devices, IoT devices like drones and any smart IoT application devices, or smart sensors in a car dashboard, or might be in a satellite application, or might be in a machinery applications in industrial scenario, or in a marine boat applications where it will show us on a navigation system. So it can be used anywhere wherever the PCB design application exists. Going to the let me just show you once this is done. Yeah, so we have got all the required outputs which has been added, and this has been passed. You can see it, whatever the report format which we have selected, including Gerber extended. So we can see it here, the PCB bill of material format. So this has got various bill of materials with a description, library reference, designations, footprint references, comments, everything inside this in a XLS format. Whatever the format as we select, we can select as PDF format, CSV format, XLS format, text format, all these formats. Similarly, NC drill file formats. This is a text format which will be giving us the XY direction part of it, so which is an output or an input to the manufacturers. AutoCAD PCB. So we can also see this one, the board which has been no, associated, which we can add it in the AutoCAD formats. So if I open it, it will be opening using the e-drawings just to show me. So let us see it how it is. So whatever the PCB board which we have designed, so everything along with the drill board, which is coming into the DWG format. Similarly, we also have the Gerber extended, Gerber format, and Gerber extended formats. As we see, so all the top, bottom, every layer which we have used inside our PCB design will be reflecting back here. Fine. Similarly, the ODB++ file export into step formats, the step format to exchange with any other CAD users. Pick and place. For the pick and place machine, this is an input for the pick and place machine. If I just open it, so these are the XY directions in mills. It has been indicated where exactly the components are coming, and then the reference XY coordinates reflecting here. Similarly, the libraries and 2581 format also is a single file format as we see it. Can be used as an advanced advanced file format developed by the Institute of Printed Circuits, and the standard has been given as 2581. So it's a single file format which the recently the manufacturers are preferring to manufacture the board. Okay, so once we have done this, even all the outputs which we have used in our design, which can be produced for a better manufacturability. Okay, so this completes the PCB demonstration from SolidWorks PCB. I hope you like it. And this is the last slide of our presentation today. So as I explained, so for a particular component need to be manufactured, there are various design aspects need to be involved. There are various design teams which will be working together for a combined or for a single product. So SolidWorks do have all the necessary products to build a complete product for a industry. So SolidWorks have the mechanical design software to design the mechanical aspects of a product, and we also do have SolidWorks PCB to address the electronic design capabilities, and we also have the data management SolidWorks PDM, which is nothing but enterprise PDM professional, which helps the engineers to manage their data efficiently. And we also have electrical design software, which is SolidWorks Electrical, which connects various electrical elements or items inside the control cabinets, or might be connecting two PCB boards and connectors and then running a harness into it. Similarly, SolidWorks also have solutions like FEA to do the FEA simulation, plastic part design, plastic injection molding, and inspection tools for the quality assurance, and visualize for the rendering of the the components or the devices which we are using it, equipment which we are using it, and the technical communication software like Composer, which also helps the companies in making their user manuals or maintenance manual, the documentation easily. So these are the various products of SolidWorks, makes the SolidWorks ecosystem very robust in every aspect of the design for a complete product design for any kind of an industry throughout the world. So with this, I'm concluding my session on SolidWorks PCB for today. Hope you like it. Thank you so much.